Hey everybody, wanted to spend a little bit of time going over metals and how they react and how to name some of the more complicated metal compounds, and even talk a little bit about something called isomerism. But in this video we're going to talk about determining oxidation states of transition metals. One of the things that we should know is that transition metals don't have a set charge. Something like sodium, which is not a transition metal, and we can go here and I will explain. Sodium is not a transition metal. So sodium, we know, will always have a charge of 1+ when it forms an ion. But the transition elements here will always have, not always, but will mostly have a varying charge, and it depends on what kind of compound it's in order for you to determine the charge that it is. But it turns out that, well, let me back up. So for example, iron can have a 2+, it can have a 3+, sometimes, but not very often, it can have a 6+, and even very rarely can have an iron 4+. Okay, so there's all sorts of options for this element to have different charges. If we're going to try to determine what the charges are, let me get rid of this writing, we have to remember a little something about electron configuration. And so, at the very minimum, what we need to remember is that the transition metals occupy the D elements, and they occupy, the electrons occupy the S elements. So if you have something like titanium, titanium has an electron configuration of 4s2. It has the electron configuration, it has argon, because it starts here, those 18 electrons, and then 4s2, and then 3d2. And we know that it's 4s2 because there's 2 elements here, and we know that it's 3d2 because there's 2 elements here. Okay, and so we know it's 4 because it's 1, 2, 3, 4, and we know it's 3 because the D elements are shifted up 1 from the S's. So that's a very quick overview of how to determine electron configuration. Let's go back here though. And so what we know is that ions form when certain electron configurations are stable. And so there are 3 conditions of stability, and that is when the electrons okay, that is when the electrons occupy all of the spaces in a shell, or they half fill the space, the orbitals in a shell, or a subshell, I guess, and then that subshell is empty. So I guess what I'm saying is, again, if we're looking at that titanium example where we have argon and then 4s2, 3d2, and so now if we go to draw the orbital diagram, 4s, and then the D's, remember the D's and S's are very close in energy, and so that is 3D. And so remember the 4 S's there's only one 4s orbital, so we draw one line. There's 5 D orbitals, so we draw 5 lines representing each of those orbitals. And then because there's 2 electrons, we draw 2 arrows pointing up. Okay. Now this is not this is not a lesson in electron configurations, but what we can do is we can use this to predict what ions of titanium will be stable. Okay. And keep in mind, this is a prediction of plausible and possible charges and not charges that actually exist. There's a ton of different variables that go into determining oxidation states of transition metals, but this is one of them. And I think it's a pretty strong factor in determining these things. So remember that metal ions are going to lose electrons. And so how are we going to lose electrons in order to meet one of these conditions of stability? Well, what if we lose 2 electrons? Okay, by losing 2 electrons, these electrons go bye-bye here. And so that would be titanium 2 plus. And if we look, these electrons here, that is an empty orbital, or not orbital, but subshell. These guys here occupy a full subshell. So titanium 2 plus is a possible ion based on electron configuration. Okay, and then the last thing that I wanted to make sure that I point out here is that we can rearrange electrons in order to promote stability. My favorite example here is for something like chromium. Okay, and copper and silver all do this. Chromium, if we're going to write an electron configuration, chromium has an electron configuration of argon, that's its core, and then 4s2, right? 1, 2, and then 3, 1, 2, 3, 4, 3d4. That's not a stable, that's not the most stable electron configuration. Okay, let's go back to our PowerPoint here. Okay, so chromium, and I always draw this like this. I always do this, the element symbol, and then the core, which is the previous noble gas, followed by the elements, or followed by the valence electrons. So remember, it's 4s2, 3d4. Now, if we were to draw this, I ran out of room. Let me take this and move it over a little bit. Okay. I wonder if I can do anything with that. Nope. Okay. So here we go. There's the 4s, and then the 1, 2, 3, 4, 5. Okay, so that's the 3 Ds. Now, if we were to draw this like this, we would get 1, 2, 3, 4. This guy here is filled, so that's stable. But this is what I call stupid filled. It's not half filled or fully filled or empty, so it's not necessarily stable. What we can do is rearrange these electrons, because these electrons are close in energy, so we're not losing much by rearranging the electrons, and this electron is going to go here. And so we still have those 6 electrons in the valence, but they rearrange in order to form this electron configuration. Now I say this because now we can do this in when we're forming ions as well. If the electrons can form a stable configuration, then likely it's going to form that stable configuration where both things are half filled, or the S's are fully filled and the D's are half filled, or something along those lines. So that is what we're going to do. So now what we can do is we can predict plausible charges on elements based on their electron configuration. So I have a sample problem here where I ask to predict, and remember, this system just predicts the charges. Ooh, I had the hiccups. Predicts the charges. It doesn't necessarily give. It doesn't give all the possible charges, and this is just one way that we figure this out. Okay, so we're going to do manganese here. Okay, and so manganese is element number 25. So the electron configuration here is argon, and then 4s2, and then 3d5. So if I'm going to look at this, I'm going to, in terms of orbital diagram, 3d, okay, this is the element, okay? We want to figure out what the charges or the oxidation states are. So now, metals lose electrons. So if we are going to lose electrons, and I'll just cross them off to try to show you how this is going to work. Okay, what if we lose one? Can we lose one here? Yes, of course we could. We could lose one from here. But what does that give us? This gives us a filled orbital, fine, stable, but then this guy here only has 4 electrons. It's not half filled. It doesn't have 5 electrons in it. So, or not orbital, but subshell. So what we're going to do is, instead of losing 1 from the D's, we're going to lose 1 from the S's. Now both of these are half filled. And that is, so that is a possible or plausible charge. And so that is going to give us a manganese, Mn, and then a 1 plus. So that's 1, but we need to come up with 3. Okay, well, we've lost 1. This is the electron configuration. What if we lose 2? Does that make a stable electron configuration? I think it does, because this guy is half filled, and this guy now is empty. So that's going to be Mn 2 plus. Okay, and then last, a third one. Let me get rid of these X's just to make sure that everybody's on the same page. And again, this is the stable electron configuration of the element. But now if we're going to lose something more than 2 electrons, what if we lose 1, 2, 3, 4, 5 electrons? Now this is filled, and this subshell is empty. And that is, again, a stable configuration. So that's Mn 5 plus. Okay, and now if we wanted to keep going, you could lose this one, and so that would be Mn 6 plus, or we could lose all of them, and that would be Mn 7 plus. So all of those are possibilities for the charge on manganese. We'll do the same thing now for iron. Iron has an electron configuration. Let's just double check it here. Iron is this guy, so that's 26. It's right next door. Okay. Some of you even may know some iron oxidation states. Just even from this video, I think I went over one. But so let's do iron here. Let me get rid of manganese because we've done that. Okay, but iron's electron configuration is argon, and then 4s2, 3d6. And again, if I'm going to draw the orbital diagram, I'm going to go 4 s's and 3 d's. Now, I get that I've used all these examples. I've used 4s and 3d, but we could use 5s and 4d or 6s and 5d. We're probably not going to use those, but you know, we can use the next row down. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So what are some charges of iron that we could predict that could be possible based on electron configuration? Well, what if we lost 1 electron? Sure, that's going to give us Fe1 plus. Again, this is filled, this is half filled. Okay, so now what if we lose 2 electrons? We're not going to lose a second one from here because that's going to make that what I call stupid filled. Okay, that subshell is definitely going to not want to necessarily be that way. But if we lose one from the S's, so now we have a half-filled S and a half-filled D, and so that means that Fe2 plus is possible. Can we lose a third electron somehow? Sure can. We can lose a third electron by removing that, so we can do Fe3 plus. And just as a little aside here, these two irons are the most common ions of iron that there are. We could lose, let's see, let me erase these guys. Okay, it's not that we're losing them, I just don't want the X's there anymore. We could lose all 6 of these, okay, to get Fe6 plus. We could lose one of these, another one, so that's Fe7 plus, and then we're stretching here, go Fe8 plus. Typically we don't go much above F7 plus. And in real life, this is a very uncommon form of iron, but it still exists. Okay, we're just predicting based on electron configuration. This, and this, for other reasons that we're not going to cover here in this video, don't form ions. But based on what we're learning here, makes sense based on electron configuration. So that is how we can predict charges on transition metals, and I think that that's a pretty neat process. So have a great night.